Okay. So there's a really important theorem in statistics called the central limit theorem, which uses the ideas that we were just talking about. So the central limit theorem is the foundation for the inferential branch of statistics, which is really what we're focusing on now, trying to make inferences about that population. The theorem describes the relationship between the sampling distribution of the sample means and the population that the samples are taking from. Okay, so again, we're focusing on this special sampling distribution where we have all these means already pre-calculated and they kind of form their own data set. So that's what we're looking at here. So this is what the central limit theorem says. It says if random samples of size n, where n is greater than or equal to 30, are drawn from any population with a mean mu and a standard deviation sigma, and the sampling distribution of the sample means is approximately normal. The greater the sample size, the better the approximation. So what we're saying is that if we have large enough sample sizes, so 30 or larger, and again, we're sampling over and over again from the same population, so we're looking at the same study, but doing multiple samples, then what happens is those means end up forming more of a bell curve. So again, it's not the original data is necessarily bell curve shape, but those means are bell curves. So again, we have a whole bunch of means that are our new data set. If random samples of n are drawn from a population that is already normally distributed, then the sampling distribution is normally distributed for any sample size, okay? So for the first one here, we need n is greater than or equal to 30 is for any population, but there is no size restriction on this theorem if the population is already normally distributed. So if you have a population that's already normally distributed, maybe like heights or weights, which are pretty standardly normally distributed, then you can have smaller sample sizes. So you could have a sample size of 10, and the means are still going to be more bell-shaped when you have a whole bunch of them put together. So what's the point there? So the point is that we can use these shortcut formulas, the ones that we just did. So in either case, the sampling distribution of the sample means has a mean equal to the population mean, and the sampling distribution of the sample means has a variance equal to 1/n times the variance of the population, and a standard deviation equal to the population standard deviation divided by the square root of n. So you have these two formulas here as well. So again, it basically says that it is okay to use these shortcut formulas that we used in our last example. You either need larger sample sizes, or the population needs to be already normally distributed. And then the means themselves will form more of a bell-shaped curve. And you have pictures right here. Okay. So the example on the left is kind of the first situation. So here our population is clearly not bell-shaped. It's like it's all over the place. I don't even know what shape it is. So if you're taking samples of size at least 30, and again, we're taking lots of samples. So I have all these data points are now means of all the samples. Then those means form their own bell curve. If your population is already normal, then you don't need large sample sizes. Any sample size is fine. And you'll see that the means, again, will form a bell curve. So the hardest thing here is to keep in mind that we're not looking at regular data here. We're looking at means. So I have a whole bunch of means, and that's my data set. All right, let's look at some examples. A study analyzed the sleep habits of college students. The study found that the mean sleep time was 6.8 hours with a standard deviation of 1.4 hours. Random samples of 100 sleep times are drawn from this population, and the mean of each sample is determined. Find the mean and standard deviation of the sampling distribution of the sample means. So first of all, in the population, I know that the mean of the population was 6.8 hours, and the standard deviation is 1.4. So again, this is on the population. And they're giving us the graph of the population, so you can see it's not normal. It's not bell-shaped. It looks like it's pretty skewed here. So in order to use the central limit theorem, we usually abbreviate it as SLT, so central limit theorem. We need sample sizes of at least 30 to use the formulas. Okay, that's basically what it says. So to use those formulas, you have to have at least a sample size of 30 here because our population is not normal. Well, we're okay because our samples are going to be 100. So our sample sizes are going to be 100. And we want to find the mean and the standard deviation of the sampling distribution of these means. So we're looking for the mean of the sampling distribution of the means and the standard deviation of the sampling distribution of the means. And again, because we're okay, because our sample size is big enough, basically what it says is that we can use these formulas. That's all the central limit theorem says. If your sample size is big enough, or if it's already normal, then you can use these formulas. So that's what you have to check. So I'm going to just rewrite my two formulas here. So I have them. Okay, so for the first one, it says that the mean of the mean of the means is equal to the original population mean, which is 6.8. So 6.8 hours. And then the standard deviation is going to be the original standard deviation 1.4, but divided by the square root of n. And our n here is 1. So this becomes 1.4 divided by 10, which is 0.14. So you're going to see that typically your standard deviation is going to get smaller than your population one, right? Because we're end up dividing here. So we're dividing, we get that 0.114. So these are the two values that they're looking for, right? So basically it just says that instead of having to find all those samples ourselves, calculate all the sample means ourselves, run it through our calculator or do the probabilities out ourselves and everything, it's a lot of work. Remember the last example we did was a lot of work and that was only a population of 4. So it gets to be quite tedious. So now if we have these formulas, then we can find our answers very quickly. The last thing they wanted us to do is to sketch a graph of the sampling distribution. So I figured that was easiest just to show you guys the picture in the book. I am not the best artist. So here's that picture we're looking at. And then here is your picture. So your mean is the same as the original. So it's at that 6.8 hours. So you can see the center is here at 6.8. And your standard deviation is super small. It's 0.14. It's, less than a quarter. So that's why this is so smushed together, is because your standard deviation is so small. So those values are really, really tight around the mean. And again, those sample means are going to be bell-shaped. So that's why you have that nice bell-shaped curve here. Okay. Assume that training rates of all 20-year-old athletes are normally distributed. Okay, so we're told that the population is normally distributed. So when that happens, there is no size restriction on samples to use the central limit theorem formulas. Okay, so if your population is already normal, then there's no size restriction you have to worry about. The mean is 135 beats per minute, and the standard deviation is 18. So our mean is 135, and our standard deviation is 18. And again, this is for the population data. Okay. Random samples of size 4, so for our sample, our n is equal to 4 here, which is okay because, again, our population is normal, so I don't have a size restriction. The mean of each sample is determined. Find the mean, standard deviation, and sampling distribution, and then also, again, sketch the graph. So I meet all my criteria to use that central limit theorem formulas. So my mean here for the means is going to be the same as the original. And my standard deviation is going to be the original divided by the square root of n. So the mean of the means is still going to be 135. And the standard deviation of the means is going to be that 18 divided by the square root of 4 here. This is 18 divided by 2, which is 9. So same mean, you're going to have the same center, but again, you're going from standard deviation of 18 to 9, so it's going to be clustered tighter together. So your means tend to be clustered pretty tightly around that center compared to your original data. And again, I'll just show you that graph real quick in your text. I think that'll be just easier for you guys to see. Okay, so it's just right over here in your text. You can see that center's at 135, and then your standard deviation is 9. So most data is going to occur within 2 standard deviations, so that plus or minus 18, and then particularly 3 standard deviations, so plus or minus 27. So you do see like that 27 mark is pretty close to that 160 value, and same thing down here, pretty close to that 110. So most of your data is going to be underneath with 3 standard deviations, and that would be your graph. So the sampling distribution for those means is going to be bell-shaped. It's still normal as well.